In this video, I want to explain work from the standpoint of energy. And the short definition, just to get things started off, is that work is when energy is transferred from one form to another. Okay, so let me first kind of reflect on that statement for a minute. We talked about conservation of energy, and we talked about how in the grand scheme of things, you can't create or destroy energy, but the energy can kind of flow from one place to another, and it can flow from one form to another, like back and forth between kinetic and potential energy, for example. That flow of energy from one form to another is what we call work in this standpoint. So it's basically energy in motion, energy that's being specifically mechanical transfers, which is all we're talking about right now, mechanical transfer of energy from one form to another. Let me give you a very simple example to start out with. Okay, let's say I have this block, and the initial state is that the block is sitting here on my hand doing nothing. And then the process I want to describe is that I grab the block, lift it up, and the final state is that the block is up here being held at rest by my hand. Okay, let's describe that process in terms of energy. So first thing I would do is draw my initial and final pictures. So my initial picture is that the block is sitting on the ground, and it is sitting on the ground at rest with zero velocity. Let me just make note of that in the picture. Okay, and then I draw my final state. And my final state, like I described, is that the block is now lifted up to a certain height above my hand, above the surface. Oops. The block is lifted up to a certain height above the surface, and it is once again at rest because I'm just holding it stationary. So again, the process I'm describing, initial state is this, final state is this. Okay. Now, let me just, without introducing anything new, let me try to describe this using the energy-based framework. Okay. The relevant types of energy here are going to be, well, you can always say that kinetic energy is kind of relevant in a way, but in this case, it's not very interesting. We have initial kinetic energy 0, and we also have final kinetic energy 0, because the object is at rest in both the initial and the final state. When it comes to potential energy, we're talking about gravitational potential energy here. So if I set the reference level to be the level of my hand, then I would have initial energy is 0 because h equals 0. H equals 0 is here. And then for the final state, I would have mgh, the mass of the block, times g, times the height that I raised it above my hand. So now, if we take the total energy in the initial state, you can see that it's 0, 0 plus 0. If we take the total energy in the final state, we've got 0 plus mgh is mgh. And then, now you notice you have a little bit of a problem here. Energy is not conserved in this process, or at least energy does not appear to be conserved in this process. In fact, so you don't have initial energy equals final energy like you would expect. What you have instead is that the initial energy equals the final energy minus mgh, because we ended up with more. Or if you prefer, maybe it would be a little bit easier to write it the other way so that we don't have that negative sign confusing us later. We can say that I am going to call mgh the work that was done on the box. I'm claiming right now that that mgh, that energy change, is the amount of work that was done on the box. And so the amount of work that was done on the box has to be added to the initial energy to get the final energy. Or in other words, if we move initial energy to the other side of the equation, we get that the work is the change in energy. Okay, so as advertised, work is a change in energy. Work is a transfer of energy. Work is a flow of energy, however you want to say it. Okay, now, that's not the whole story, though. That's just one example. Let me do another very, very simple example. Let's do the opposite process, where the block starts out above my hand, and I release it from rest and let it fall down. And I'm going to consider the final state to be just before it hits my hand. Okay, I'll switch pen color for this, just to make it clear that we're doing a different problem now. I'm going to leave the other one there. So this time, my initial state is that the block is up here at rest, and the final state is the block is now down here, about to hit the ground, traveling downward at some final velocity. Okay. Now, we know how to calculate what that final velocity is, et cetera, et cetera, et cetera, but right now I just want to focus on looking at how the energy is behaving here. So I have, in this case, the initial kinetic energy equals 0. The final kinetic energy is not 0. It's half mv squared. Remember, it's not negative half mv squared. Kinetic energy is positive. We'll have initial energy, potential energy is mgh, and final potential energy equals 0. So we have here the initial energy is mgh. The final energy is half mv squared. And we apply conservation of energy to this problem, and then we could solve it if we wanted to and find out what the final velocity is, or whatever the case may be. Now, what makes this problem different from this problem? There actually is still work done in the red problem that's on the right of the screen. There actually is still work done. But in this case, the work is not changing the total energy of the system. Because remember what I said, work is basically a transfer of energy from one form to the other. You'll notice here there is a transfer of energy, but in this case, the transfer of energy is it's going from potential energy to kinetic energy. So there is a transfer of energy, but it's internal to the system. It's just between the different forms of energy within the system. Rather than on the left in the black problem, the transfer was kind of this magical transfer of energy into the system from my hand, basically. But in the red problem, it's just a transfer within the system. So how would you calculate this transfer? Well, you could calculate it either as the change in the system's kinetic energy, because the kinetic energy went up by this amount, but also you could calculate it as the negative change in the potential energy, because the potential energy went down by exactly the same amount of how the kinetic energy went up. And you get, well, in the broad sense, you get a very simple conclusion that work is a change in energy, that work is a transfer of energy. But when you start getting into specifics, you get a little bit of a confusing result here, that I have 3 different equations on the screen. One says that work is equal to the change in total energy. One says that work is equal to the change in kinetic energy. One says that the work is equal to the change in potential energy, negative. So how can all those statements be true simultaneously? Well, maybe that'll be the subject of another video, because that'll be kind of a long answer. But from this video, I just want it to first sink in that the overall concept is that work is a change in energy. Work is a transfer of energy. That's the main concept of understanding work from the energy framework. And that transfer of energy can either be into the system to change its total energy, like on the left, or it can be internal to the system just a transfer between the potential energy and the kinetic energy, like on the right.